right, welcome to your notes video. So our next big topic in this class is Boolean logic and circuits. So we started with data representation, which is just, how do we actually represent information on the computer? And we kind of settled on this idea of everything is represented as ones and zeros. But we sort of treated these ones and zeros as just like abstract things. Well, the ones and zeros are actually electrical signals, all right? One is high voltage, zero is low voltage. So what we're going to look at in this unit is how those electronic signals pass through the computer and perform various operations. So like, how do we simulate addition by sending electrical signals through a circuit? What does that look like? And to do that, we're going to have to learn a little bit something called Boolean logic. All right. So this activity right here at the start is just to sort of get us in the mindset. All right. So it says you're searching the internet and you run a search for ravens or crows. And you get back 200 pages. All right. You then run another search on ravens and crows on the same 400 pages. So yeah, I didn't underline that at the start, but there's 400 pages in total. All right, so there's 400 in total. We searched for ravens or crows. We got 200 back. Now we're searching for ravens and crows. So I want you to take a minute, pause the video, and think about what are the possible results that we could get back. If we know that we got 200 results when we searched on ravens or crows, what are the possibilities when we search for ravens and crows? Could we get 400 back? Could we get 300 back? Could we get 200, 100, 0? You don't have enough information. But pause the video, give it some thought, and make your guess. All right, so let's see how we did. So ravens or crows basically means that we don't care which. As long as one of those words show up, we're happy. All right, ravens and crows implies that we need to see both of those words on the page to return the search result. So when we're saying how many could we possibly get back, we can't get back 400 because there's no possible way that there's 400 pages that have both of these words if there are only 200 pages that have this word or this word. All right. By the same logic, it couldn't be 300. Now, let's take a look at the other ones here. Now, if there were 200 pages that have ravens or crows, there's a few different ways this could break down. It could be 200 ravens and 0 crows. It could be 0 ravens and 200 crows. It could be 200 ravens, and on those same 200 pages, the word crow also appears. And then almost any other combination that works out in this manner where you have 200 pages in total that have ravens or crows. So this right here isn't saying 400 pages in total. This is saying that 200 pages have the word ravens, 200 pages have the word crows, and it must be that they are the same pages. So we could have 200 pages still come back. It would just mean that all of the pages that we found for ravens or crows, they all happen to have both words on them. Now, there could also only be 100 pages, all right? There could have been 50 pages that had ravens. There could have been 50 pages that had crows, and there could have been 100 pages that had both. All right, so that would be a perfectly valid result. And we've already shown that it could be 0 pages because you might have 200 pages that have crows and 0 that have ravens, or you might have 0 pages that have crows and 200 pages that have ravens. So it could be any one of those three. Can't be 300, can't be 400, and we do have enough information to determine this because we just went through it. All right, so let's take a look at the next one. If next you run a search for not ravens on the same 400 pages, how many pages could you get back as a result? Circle all that are possible. Can you explain your selection? So think about what we just talked about. Think about the logic we went through and see what you get for this one. All right, so let's go through this again. And let's think about the extremes, because I think it's sometimes helpful to think about the extremes. So we ran this query, ravens or crows. We got back 200 results, right? One extreme is that we could have ended up with 200 crows and 0 pages that have ravens on them. Now, if this was the case, and then we ran a query that said not ravens, well, it might be that there were 0 pages that have ravens. So if we say not ravens, we will get all 400 pages. All right. Now let's go to the other extreme. All right. I could say, all right, let's pretend I had, 0 crows and 200 ravens. Well, now if I run a query that says not ravens, right, there's 200 that have ravens, so that means there's only going to be 200 left. 400 minus 200 equals 200 that are not ravens. All right. So by looking at the two extremes, we can see that we can get 200, we can get 400, which probably means we can get 300. So let's think about a situation where we might end up with 300. All right. So of those original 200 results we got back, maybe 100 of them said crows and 100 of them said ravens. So if 100 said crows and 100 said ravens and there was no overlap, there were none where they were both the same, then we could say, oh, okay, then the ones that are going to be not ravens are going to be 300. So the question is, we just established that you could have 200, 300, and 400. The question is, can we have 0 and 100? Right? Well, to have 0 pages that are not ravens, this would imply that you had 400 pages with ravens. And based on this first result, we know that there's no way we can have 400 pages with ravens, so that one's out. What about 100? Well, 100 would imply that we had 300 pages with ravens. Again, since we only had 200 that were ravens or crows, there's no way we can end up with 300 pages that have ravens. So our only options are 200, 300, and 400, and obviously not that we don't have enough information to establish this. All right, so this is just getting you in the mindset. It's forcing you to think a little deeper about and ors. Because I think sometimes we think they're so simple that we don't realize that there are implications to what they actually mean. And here's what I say, we always do the example like, and, well, both things have to be true, or only one thing has to be true. And it's so in line with English and it's so in line with what we expect that I don't think we ever stop to really think deeply about it. And this sort of exercise kind of forces you to really grapple with what these words mean and the consequences that they have when you're working in sort of this finite set world of a fixed number of results. Okay, so we're in the mode, we're in the zone. Let's actually switch over to applying this to computers now. All right, so Boolean expressions, truth tables, and circuits. Chapter 4 of your book. All right, so that's the section of your book that you want to be reading. That's the section of your book that you want to be going over. Because again, it's going to reinforce what I talk about here, and it's going to give you some additional detail. So, starting off, Boolean operations. The word and, A and B. You will also sometimes see that written as like A times B. You will also sometimes see it written as just A, B right next to each other. Any one of these represents A and B. And when you're using the word and, it is true if both A and B are true and false otherwise. So if we were actually in school right now, I might say, hey, stand up if you're wearing jeans and a t-shirt. And then presumably if you were wearing jeans and a t-shirt, you would stand up. But if you were only wearing jeans, but maybe a sweater, you would not stand up. Or if you were wearing a t-shirt, but shorts, I don't know why you'd be wearing shorts, it's pretty cold right now, you would again not stand up. So you're only standing up if both of them are true. All right, so quick example here. You know, the sky, we'll just use this. The sky is blue. Now, is the sky really blue? I mean, it's just the light reflecting off the ocean that's making it look blue, but let's just pretend right now that the sky is blue and we're going to treat that as a true statement. And pigs fly. Now, I think we can all agree that the world would be a better place if pigs fly, but currently they don't. Either that or it would be a terrifying place. I'm not really sure. All right, but this is true. This is false. Since only one of those is true, the whole thing is considered false. All right. Versus, again, we're going to stick with the sky is blue. Just go with me here. We're going to consider that to be true. And grass is green. We can also consider that to be true. In this case, since they're both true, the whole thing is true. And then I think it should go without saying, but if both things are false, so pigs fly and sheep moo. Sheep don't moo, silly goose. Cows moo. This is false, so the whole thing is still considered false. All right. The old adage, two wrongs do not make a right. So that would still be false. And then this over here is just what we just talked about here. Ravens and crows. You know, because you're requiring both words to show up, you're going to end up with far fewer results. And just wait till we get to the one on the next page with or. You're going to see that number is going to shoot way up. All right. So let's look at what we call a truth table. All right. Now, we are going to use these to kind of walk through and examine the Boolean logic of our different operations that we are applying. Now, for this one, it's going to be very simple, but as we move through these notes, they're going to get bigger, more complicated, more involved. So how do they work? A 1 equals true. A 0 equals false. So with this table, we are going to list out every possible combination of trues and falses and then show what they work out to be. Right? These are going to be our inputs. This column is going to be our output. Now, when you are filling in the inputs, I expect you to do it in an organized manner. If you do not do it in an organized manner, I do not care if it's correct. I will mark it wrong because it's a nightmare for me to try to go through and see, did you actually get every combination? So what do I mean by an organized manner? All right, so here's the way we're generally going to do it. Now, I don't care whether you start with a 1 or a 0. I like to start with 0, but this part you can have a little flexibility with. So for column A, I'm going to go 0, 0. And then I'm going to, in column B, do the two different options, 0, 1. Right? Now that I've done both options in this column, I'm going to allow A to switch to 1, 1. And then I'm going to do these columns 0, 1. Now, let me just again emphasize. I started with zeros here, so I started with zeros here. I went to 1 second, so I did 1 second here. I didn't flip back and forth and go 0, 1, 1, 0. I didn't just randomly put them out. There's an organized fashion to this, and that's what I'm going to be expecting from your truth tables. Again, I don't care if they're right. I will mark them wrong if you don't put them in an organized fashion. So, fair warning. Now, with our ands, 0, 0 is false and false, so that's still false. False and true is still false. True and false is still false. The only time it's true is when we have true and true, so we would put a 1 there. And again, this is a very basic truth table, but we're going to see that they get bigger and more involved as we go. So moving on to the OR. All right, A or B. A lot of times we'll write this as A plus B. All right, so you might see it like this. You might see it like this, but you should know that plus is the OR, multiplication is the AND. All right, it is true if A or B, or both, are true, and false otherwise. So false otherwise basically implies both have to be false. All right, let's not be coy about this. It just means that both have to be false. So again, if you were in the room right now, I might say, stand up if you're wearing jeans or a t-shirt. Now, both of them don't have to be true. Only one of them has to be true. All right, you could be wearing t-shirts and a shorts, and you'd be allowed to stand up. You could be wearing jeans and a poncho, and you could stand up. Why are you wearing a poncho inside? I have no idea. That is up to you. All right. So let's go back to our silly examples here. Sky blue or pigs fly. This one's true. This one's false, unfortunately. So that means the whole thing is true. Now, if both things are true, sky blue or grass green, great. Truth is always something to strive for, but it doesn't give us any extra credit here. It just means that the whole thing is still true. The only time it's going to be false is when you end up with two statements that are false, like pigs fly or sheep moo. Those are both false. So in this case, the whole thing is considered false. Now again, going back to our ravens or crows, just notice that this number is a whole lot bigger because now we're saying, all right, you don't have to have both. If you have one, great. If you have the other, great. And if you have both of them, great. We're willing to accept any one of those as a valid result. All right, so what would the truth table look like for an OR? All right, again, we're going to put it in our organized fashion because you don't want to get it marked completely wrong. So I'm going to go 0, 0, and then 0, 1. And I'm going to go 1, 1, 0, 1 again. All right, nice and neat and organized. So false or false is still false. False or true is true. True or false is true. And then true or true is still true. All right. Which brings us to not. Basically like opposite day. Wouldn't that be crazy if I just taught every class as opposite day? So confusing. You'd never know what to believe. You'd be like, wait, is that true or is it opposite day? Don't worry, I'm not going to do that. All right, not A. True if A is false. False if A is true. Right? Sometimes you'll see this as this, right? Not A. All right. So, not jeans. All right? What would that be? Right? So that would mean that you would only stand up if you were not wearing jeans. Right? If you were not wearing jeans, then you'd be allowed to stand up. If you were wearing jeans, you would not be able to stand up. So sky blue, whoops, we already know is true, kind of. Not sky blue would be false. Sheep moo is false. Not sheep moo would be true. All right. So truth table for this, we only have one input. So this one's pretty hard not to keep organized. And not A would just flip those around. All right. Sometimes you actually also see it like this. Like that. Okay. Either one of those. All right. But most of the time in this class, we're just going to use this one. So this is the one you want to focus on. Boolean operations practice. All right, so let's take what we just did and let's practice it a little bit. So evaluate the following Boolean expressions, assuming, so I'm going to give you values here. A is 1, B is 0, C is 1. Okay. So take those numbers and then tell me, what would each of these work out to be? All right, so pause the video, give it a shot, and then come back. All right, A and B is 1 and 0, so true and false, and requires them both to be true, so this one is still false. All right, A or B. Okay, so this is true or false, or only requires one of them to be true, so this whole thing is still true. All right, this is not A. All right, this was a 1. We're saying not A. So we've got a 0 there. This is not A or B. All right, so let's go through this. Not A. This was a 1. We're doing not A. That turns it to a 0. Or B is a 0. So this is false or false, which is going to give us a false. Now, I know what you're thinking. You're thinking, Mr. Bona, didn't you just say we were going to normally use this one, not this one? Yes, it's just harder to do that on a computer. And I took the easy way out. So when I drew it by hand, I'm always going to use the line over the top. But on the computer, I sometimes do this because it's just way easier. All right, so let's take a look at this bottom one here. A, B, A, and B. All right, so this is going to be true and false. So this one right here is going to work out to be false. B and C, also going to be false. Not B is going to turn this into a 1. And C, which is a 1, that's going to be true. Now we're ORing all of these together. So false or false is going to be false. But then or true, as long as we've got that one true, the whole thing is going to work out to be true. Now, I don't want you to think this is an addition problem. Yes, 0 plus 0 plus 1 is 1. But if this had been 1, 1, 1, we wouldn't write 3 here. It would still just be 1, all right? The only options are 0 and 1. So, true. All right, 2. Find a Boolean expression that corresponds to the truth table. Write your answer at the top right of the column. So this is, can you think of something? Can you think of an expression that will yield this truth table? All right, what combinations of ands, ors, and nots could we combine so that we get a truth table where this is the only one that actually works out to be true? All right, so again, give it some thought and then come back. Now this one's a little harder, right? This was easier, just kind of going through it. This one's a little harder. Now we are going to learn a technique to make this easier, Well, let's think about this. All right, so where A is 0, all right, we're seeing that both of these are true, right? So a good place to start might be A naught, right? Because if the only expression was A naught, then both of these would be true and both of these would be false. So we're getting close, but we're not quite there yet. Right? But I know that A naught's a good start because if both of these get flipped around, they'll be true, which is what I want. Now, if this part is good, I can OR this with something, right? Because that way, when this is true, I know the whole thing is going to be true. So it takes care of these two up here. And then let's see what I want to OR it with. All right, well, if I OR it with A and B, this one would be 0. This one would be 1. Wait a second, is that all I need to do? Yeah, I think it is. All right, so if I OR that with A and B, look at this. All right, when A is 0, this becomes 1, and the second half doesn't matter. All right, when A is 0, this becomes 1. The second half doesn't matter. All right, when A is 1, this becomes 0. So now I do have to look at the second half. All right, so 1 and 0, oh, false, no good. When this is 1, this part's 0, but this part will be 1 and 1, which will give me the 1 there. All right, and again, we're going to learn a technique for this, but this was just kind of a puzzle to see if you could figure it out. You might have come up with something different. All right, this is certainly not the only solution, but this is one solution. All right, another solution might be this: not A, not B, or not A, B, or A, B. How did I come up with that solution? Well, that's what we're going to learn how to do in a little bit. All right. Consider the Boolean expression below. If C is false, what can you say about the value of the entire expression? All right. So do you even need to know anything about... All right. So I just paused the video because they made an announcement that they're going to be testing the fire alarms. So that's great. So if you suddenly hear the fire alarm going off, sorry about that. It's perfect. So if this is false, do we even care what A, B, and D are? Yes or no? We don't. All right. Why? Because this is C and all of this. And we know with an and, both things have to be true. So if I tell you that C is false, it doesn't matter what this works out to be. The whole thing is going to be false. Now, if they had told us C is true, then we would have had more information about A, B, and D. But since they're telling us C is false, the rest of it is irrelevant. All right. It's like a short circuit evaluation. Like we don't even need to know the back half because we know the front half with an and. The same can be in reverse with an or. Like once you know the first thing is true in an or, you don't actually care about the second part. With an and, once you know the first thing is false, you don't even care about the second part. All right, so computers and electricity. Let's bring this full circle. So gate, a device that performs a basic operation on electrical signals. So true, which we've been representing as 1, can also be represented as high voltage. All right, false, which we've been representing as 0, can be represented as low voltage. All right, so we talked a little bit about transistors back in the first unit, but by stringing these transistors together, we can create logic gates or circuits inside of our computer that produce the behavior that we've been talking about. All right, so we can have an AND gate, which has 2 inputs into it. And sometimes we put the dot in here just to make sure that we're very clear that it's an AND gate. And if it had high voltage on one input and low voltage on the other input, we would know that the output of this gate would be 0 or low voltage. Right? If we had the same thing, but we had 1 and 1, then we would expect the gate to produce a 1 or high voltage. All right, so we're going to start drawing these little diagrams. And when we want an AND gate, this is what we're going to be using. All right. This right here is our OR gate. Sometimes we'll put the plus sign in there, just for those graphically impaired that aren't very good at drawing things. So this is our OR gate. And again, you have your inputs. And maybe this time they're 0 and 1. And because this is an OR gate, we would expect an output of 1, or our output would be high voltage. And then over here, this is our friend, the NOT gate, which basically just flips it around. All right, so these are symbols that you're going to have to get familiar with because we are going to be using them in our diagrams. So this is going to be our NOT gate, this is our OR gate, this is our AND gate. Now, there are a few extra gates that we will sometimes see. All right, most of what we're doing in this class will be the ANDs, the ORs, and the NOTs, but those are not the only gates that exist. All right, there's a much larger world of gates that are used when you're actually designing circuits on a computer. One of those is the NAND gate. All right, and the NAND gate is basically scrunching together a NOT and an AND gate. All right, so this is basically the NOT. This, shockingly, is the AND part. All right, this is basically how we show that the AND gate is being inverted. So what's happening with this gate? Well, let's look at our truth table. So 0, 0, 1, 1, 0, 1, 0, 1. Normally with an AND gate, 0 and 0 would be false. With an AND gate, 0 and 0 is true. Normally this would be false as well. Now it's true. Normally this would be false as well. Now it's true. Normally this would be true. Now it's false. So it basically takes the results of an AND gate and it flips them. All right. A NOR is the same exact thing. This is our NOT. This is our OR. This is basically inverting the result. So normally, false or false would be false, but now it's true. False or true would be true, but now it's false. True would be false. Yeah. True or false would normally be true, but now it's false. True or true would normally be true, but now it's false. All right, so it's just taking those results and then it's flipping them or negating them. And this is called the NOR, this is called the NAND. All right, and what we'll see is like those can be useful when you're building larger circuits because you're trying to produce certain behaviors. All right, and to produce those behaviors, it might be way easier to use one of these than using just ANDs and ORs and NOTs and stuff like that. All right. The XOR gate is what we call the exclusive OR. All right. And the way this one works is, let's fill this in first, is you can only have one true. Or put another way, your inputs can't match. So if your inputs match, those are both false, it stays false. If your inputs both match, those are both true, it's false. The only time you get a true is when your inputs differ. All right, so here our inputs differ, here our inputs differ. All right. And this circuit, this gate is actually really helpful when it comes to creating circuits that add digits together, right? And we're going to see that in a little bit on why it would be useful. But this is a gate that gets used a lot for like creating circuits that can add binary numbers, all right? So again, these are just 3 other ones that you should be aware of, though primarily we're just going to be sticking with and, or, and not in this class. You know, if you were to take a circuit design class, you'd go a lot deeper. But in this class, we're just kind of giving you a survey or a taste of what's happening here. All right, so a circuit is a combination of gates where the output of one gate is used as the input for another. All right, so here would be our circuit diagram. Now, based on what we just looked at, reminder, these are our AND gates. So I'm going to put the little dots in there to show that it's the multiplication. All right, this would be our OR gates. So I'm going to put the little plus sign. And these represent our wires. All right, so these are the wires connecting those gates. So here are my different wires. All right, now this is basically just showing like this is my A input, and it goes here, and then it goes down in here. So this is A, this one right here is still the letter A, this is C, and this one would be the letter B right here. Right? It's just going straight in. Right? Now, our truth table. Right? A, B, C are straight inputs. Right? D and E aren't really, I mean, they are inputs because they input into here, but they're the result. They're outputs and inputs. All right, they're the outputs of these operations, and then they become inputs into this OR gate. So when we're creating our table and we're thinking about all the different combinations, we're really talking about the combinations of A, B, and C. Now, when you have just one variable, there are 2 possibilities. All right, true or false. When you have 2 variables, there are 4 possibilities. When there are 3 variables, there are 8 possibilities. When there are 4 variables, there are 16 possibilities. When there are 5 variables, there are 32 possibilities. Hopefully you're noticing that these are powers of 2. You know, if you have 2 variables, you have 2 to the 2 possibilities. If you have 3 variables, you have 2 to the 3rd possibilities. If you have 4 variables, you have 16 possibilities, which is 2 to the 4th. All right, so how many variables you have is how big your truth table needs to be. Now, again, I expect it to be organized. All right, so let's talk about how we will do one when there are 3 variables. So instead of having 2 zeros, I'm going to have 4 zeros. Right? And then what I'm going to do is for B, instead of going from 0 to 1 here, I'm going to say, oh, 0, 0, and then only C, which is the last variable in line, rotates every time. Right? So I've gone 0, 0, 0, 0, 0, 1. Now I can go 0, 1, 0. Now I can go 0, 1, 1. Now, if I go down here, 1, and then I go back to what I was doing before. So this would be 0, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. And hopefully in this bigger chart, you now know why I think this is organized and why I would start at 0 as opposed to 1. I'm just counting up in binary, right? This is 0, this is 1, this is 2, this is 3, this is 4, 5, 6, 7. So I'm putting it in binary order so that it's organized, I don't accidentally miss one, and it's easy to keep track of. All right, now let's see what actually happens. All right, so again, these are my inputs. And let's see what happens. So D is the result of A and B. All right, so an AND requires both to be true. All right, so they're not both true, so it's 0. 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 They're both true. They're both true. All right. E is the output of A and C. So again, we're going to do the same thing. Are they both true? Nope. 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 Yes. Nope. Yes. All right. So I've got my inputs. This is sort of my intermediate. All right. It's part of the circuit. It's both an input and an output. All right. It's an input to this gate. It's an output from these gates. Now our final output is the ORing of D and E. All right. Well, we just saw that ORing is only one has to be true. So is one of these true? Nope. 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 One is true. Okay, so there we go. One is true. There we go. Both are true, but that's still okay. So there we go. Right. So this informs us how this circuit will actually behave. All right, and this is my final output right here. All right. And this runs through all of the possibilities. So if I give you like an input of 1, 0, 1, that would correspond to this row of the table. And we've accounted for every single possibility. So now we know how this table is going to behave and how it's going to perform no matter how we do it. If we build this circuit, this is the behavior that we're going to get. And the idea is eventually not just to build random circuits, but to build circuits that achieve the behavior that we want. And that behavior might be adding things, it might be subtracting things, it might be dividing things, it might be doing all sorts of different operations. And we're using those to get certain behaviors on the computer. All right. Combinational circuits. Consider the Boolean expression A and B or C. All right, so B or C is happening first because it's in parentheses, and then we're taking the result of that and we're ANDing it with the input A. Draw its circuit diagram on the left, fill in its truth table on the right. Okay. So let's see. We need an AND gate, and we need an OR gate. So I'm going to draw my OR gate. Don't make fun of my OR gates. All right, there's my OR gate. I'll put a little plus sign in there so that you know that it's an OR gate. All right, B and C are feeding in to this OR gate. All right, those are the two inputs into our circuit. The output of this is then going into an AND gate. Right, there's my little multiplication sign, so you know that it's an AND gate. And the other input to this AND gate is my A input. This would be my final output. All right, so this would be a circuit diagram for this expression right here. All right, and that's a skill that you're going to need to, we're going to develop over the next week or so, is taking an expression and drawing the diagram, taking a diagram and writing the expression. All right. But what I want you to do is take a second and try to fill out the truth table for what's going on here. All right, so hopefully you gave this a shot. Tried to figure out this table. Now, let's see what it was. All right, so again, we're just counting up in binary. 0, 1, 2, 3, 4, 5, 6, 7. All right, now, A and B or C. And needs both of them to be true. So these first four where A is false, I don't have to care about B or C because I know that they're going to be false. Now, down here, I have to start caring, right? A is true, but B or C is false, so the whole thing is still false. A is true, B or C is also true, so the whole thing is true. A is true, B or C is also true, so the whole thing is true. A is true, B and C are also true, so the same thing is true. Now, hold up, because that looks awfully familiar. All right, that looks a lot like the one we just did. I would say that it looks almost identical. I mean, not almost identical, it looks identical. It's the same exact truth table. All right, so what's happening here? All right, this is called circuit equivalence. Two circuits that produce the same output for each combination of inputs. So we had this one, A, B plus C, produce the same thing as, all right, let's see if we can figure out what this is. This is A and B ORed with A and C. So A, B plus A, C. All right, that's what this circuit would be right here. A and B, A and C being ORed together. Now, I don't want to go too deep into this because this is not a circuit design class, but there are times when you can do algebra-like modifications to these to help simplify your circuits. And again, I say algebra-like because it's not quite algebra, but in the sense of AB plus AC, we kind of do a little reverse distributive or factor out. We could see how that could be the same as A, B plus C. All right, so again, these two circuits are equivalent, which means they're producing the same output, even though, you know, visually they might look different. And like, obviously, this would be the better circuit to design because this circuit only requires one AND gate and one OR gate. The other circuit required two AND gates and an OR gate. And that's another thing, like you're designing circuits, you're trying to fit things on chips, you're trying to make it smaller and smaller and smaller and smaller, right? The more efficient you can be with your circuit design, the smaller you can make the chip. If I can do the same exact operation with 2 gates as opposed to 3 gates, I've just saved room on the chip and I can use that room for other things, or I can take that space and make my device smaller, all right? So again, we're not going to get deep into that, but there are some times where it's pretty easy to see how we could sort of make things simpler. So I said back on the problem where I was like, try to figure out what this would be. And I said, oh, here's another possible solution for it. I'm going to show you how I got that possible solution. And this is a technique you're going to be able to use and you're going to be expected to use going forward. So it's called the sum of products circuit construction algorithm. Right? Not a mouthful at all. Rolls right off the tongue. All right. This 4-step algorithm takes you, yes, you, from a truth table to a corresponding circuit of AND, OR, and NOT gates. So exciting. All right. This algorithm will guarantee success or your money back, but the circuit may not necessarily be optimum or pretty. And by optimum, I mean minimum number of gates. Now, the or pretty part, I feel like that's objective. I mean, by objective, I mean subjective, because maybe you think the gates are very pretty and beautiful, and who are we to judge for your personal preference when it comes to circuit diagrams? All right, so again, take the pretty part with a grain of salt. All right, how does this algorithm work? What do? We start with the truth table. We always start with the truth table. Right? Everything starts with the truth table. Truth's important. It's the bedrock of any good computer. Step 2, identify rows with 1 for an output and form the product and together the input variables, negating each input variable that is 0 on the row. That's a mouthful, so let's actually talk about this. So this is not A, not B. The reason it's not A and not B is because those are zeros. If we AND together two not A's and not B's, or we AND together two not zeros, it's going to give us a 1 for an output. So if I say not A, not B, and AND those together for this line, well, not 0 is 1, not B is 1, ANDing 1 and 1 together is going to give me a 1. So this one expression takes care of this 1 that I'm looking for right here. All right, if I'm trying to get this 1, I'm trying to produce this 1, I could say to myself, all right, well, this is not A, and then regular B, right? Not A turns that into a 1. I don't need to flip this one around because it's already a 1. And if I AND those together, it'll be 1. Right? This one has an output of 0, so I don't have to worry about it. This one, they're both already 1s, so I'm not going to have to negate them. I can just say A and B. Now, I know that this one will produce the output that I'm looking for. If I feed a 0 and a 0 into this expression, it'll give me 1. If I feed a 0 and a 1 into this expression, it'll give me a 1. If I feed a 1 and 1 into this expression, it'll give me a 1. So what I now know is that if any of these are true, the output will be true. Right? And that's going to be important when we get down here to step 3. So we identified the rows that had a 1 for the output. 1, 2, 3. We formed a product. Right? These are all products. They're AND together. I can draw a little dot if that helps. The input variables, and we negated each input variable that had a 0 on the row. So A had a 0, so we negated it. B had a 0, so we negated it. A had a 0, so we negated it. B we left alone. A and B we left alone. Step 3 is form a Boolean expression by summing, ORing together the terms from step 2. Right? That's where this comes into play. If any one of these is true, the whole thing is true. Well, that describes an OR situation. So if I say not A, not B, or not A, B, or A, B, this will give me a circuit that will produce this behavior. Right? And I know it'll produce this behavior because if I feed a 0, 0 into it, I know that this is going to be true, and then I don't care about the rest of it because it's an OR. I know that if I feed a 0, 1 into it, this will be true, and then I don't care about these two because it's an OR. It'll be true. I know if I feed a 1, 1 into it, this will be true, and I don't care about the rest because it's an OR. Right? By individually accounting for every single one and then ORing them together, I know that it'll work. Again, it's not going to be a great circuit. It's going to be pretty inefficient, but it will work. Right? This will be a functioning circuit that will produce this behavior. Now, again, it's not the simplest circuit. Right? This algorithm is not going to produce the smallest circuit possible. Here, let me just illustrate one way that we could simplify this. And again, I'm going to do algebra-esque stuff just to illustrate the concept. You do not have to worry about this, all right? When I ask you to do this algorithm, you don't have to simplify it, but I just want to show it to you so that you're aware of it. All right. I believe in showing it to you, even if I don't expect you to do it. So notice how both of these have an A naught. So I could pull out an A naught and rewrite this as A naught, B naught plus B plus AB. All right. All I did was pull out the A naught from both of these. Now, if we think about this expression, B naught or B, this is an or, and it's saying B or not B. Well, if one of these is 0, that means this one has to be true. If this one is true, this one has to be false, right? There's no possible way you could ever have this be false or false because you're knotting them. So this part becomes irrelevant, right? Because this part's always going to be true. So since it's always going to be true, we can just drop it, and then we have a circuit like this. All right. This circuit will produce the same behavior as this circuit. This circuit uses 3 gates, not gate. So I guess one for the and, one for the or, one for the not. 3 gates. This one's using 1, 2, 1 for the and, 1 for the or, 1 for the not, 1 for the or, 1 for these nots. So this is obviously a much shorter, less involved circuit than this, but they will produce the same behaviors. Now, again, this is extra. You do not have to worry about this. This is not something you're going to have to do, but it just shows that you can often simplify what this produces. This is rarely the ideal circuit, but it works. All right, this circuit will produce this behavior. All right, so step 1, make your truth table. Step 2, find the rows that are 1s, create these little short expressions. Step 3, OR those expressions together. Step 4, draw your circuit diagram. All right, so that's the 4-step process that we are going to use. Now, sometimes these diagrams can get messy or involved. Here's one way you can draw them that sometimes makes it easier to keep things neat. So we can start with an A, and then we can draw a vertical line down this way. Then what we can do is we can go over like this, do our NOT gate, and draw a second line down for not A. Then we can do the same thing for B. All right, here's our B. And we can go off to the right here, make our NOT gate. And this would be our not B. All right, now, how does this help us and how do we use this? All right, so this is the gates that we're trying to make. So we've got 3 AND gates. So I'm going to make my 1, 2, 3 AND gates. All right. The very first one is not A, not B. So what I can do is I can make a little dot here and say, all right, this one goes here. I can make a little dot here and say this one goes here. And it's easy for the viewer to see that, like, okay, this is feeding in from the not A and the not B, and I don't have lines crisscrossing all over the place. All right. Then I could do not A for the second one. So I'm going to make another dot down here. That's going to feed into not A. And then I've got regular B. So that's going to just tap into this line right here and go over. And then the last one is just A and B. So I'll put a dot here. I'll send that right in there. I'll put in a dot here. And I'm going to send that in right there. And now I don't have lines like crisscrossing all over the place. It's very easy for somebody to look at my diagram and say, oh, this one's A and B. This one's not A and B. This one's not A and not B. All right, and these are all ands that are feeding into them. And then the OR, All right, so here's the deal. In this class, to keep our diagrams simpler, I'm going to allow you to feed 3 gates into a single OR gate. All right, so I'm going to allow you to go 1, 2, and 3, and draw your diagrams like that. All right. A more precise way to draw this diagram would probably be to do this. So let's pretend these were your 3 AND gates. I would probably have 2 go into here, and then the output of this feed in to another OR like this. Now, I'm not going to make you do that. I'm going to just let you put the 3 inputs into the OR gate here. So when we're doing this sum of products algorithm, when you have everything feeding into an OR gate, you can just have it feed into the one OR gate. You don't have to show them like cascaded like I'm doing up here. So we've got our 3 pieces, 1, 2, 3. We know that we're ORing those all together. For this class, I'm okay with you feeding them into a single OR gate instead of having to show like, okay, these 2 feed into this one has an output, and it feeds into this one, which is picking up the input over here. I don't need this level of detail. If you want to give me that level of detail, I'm not going to mark it wrong, but I'm fine with you just putting all of these into our OR gate and using that as our output. Okay? Cool. Now that that's out of the way, let's give one of these a shot. All right. And by let's give one of these a shot, I mean you give it a shot. I mean, I know how to do this. I'm teaching it. I hope I would know how to do it. It would be awkward if I didn't. So try this one on your own. The jump start that I'll give you is that the 3 rows that you need to make expressions for are this one, and this one. So make your expressions, put them over here. These are your individual terms. OR them together. Draw your diagram. Okay? So give it a shot and let's see how it goes. All right. So hopefully then for this one, you recognize that this was a 0. So it had to be not A and then just B, C. And then for this one, hopefully you recognize that A could be left alone, B would need a not, C could be left alone. And then for this final one, hopefully you recognized that A and B could be left alone, but C would need the not. All right. These are the only 3 terms that I would need because these are the only 3 rows that are 1. Now, the next step is the easy step. It's just taking these terms and adding them, technically ORing them together. So I've got not A, B, C, plus A, not B, C, plus AB, not C. All right, that would be my Boolean expression. So next step is going to be to take this and draw the circuit diagram. All right, so we want to keep it nice and neat. So we're going to use that great vertical line trick that your amazing teacher just showed you. So there's our A line. There's our not A line. There's our B line. There's our not B line. There's our C line. There's our not C line. All right, so now I have any possible input that I might need. All right, so taking that, we know that our 3 pieces are not A, B, C, A, B, not C, A, B, C, not. Again, I'm fine with you just having all three of these go into a single AND gate. You don't have to you don't have to cascade together AND gates. So we're just going to have one big AND gate that accepts three inputs. So there's one AND gate that's going to accept three inputs. There's a second AND gate that's going to accept three inputs. There's a third AND gate that's going to accept three inputs. So the first one was A naught. So there's my A naught. You bring that over to my AND gate. B. So there's my B. You're my B. And then C. See what I did here? I'm on fire today. This is good. This is so good. This is what happens when you make an hour-and-a-half long video. All right. Next one was A, B naught. I mean, to be or not to be, right? Just keep coming. They just keep coming. Woo! All right. A. I'm so sorry for you. All right. So there's our A. There's our B naught. There's our C. They're all feeding into that AND gate. And then last but not least, we had A, B, C naught. So there's our A. There's our B. There's our C naught. Right? You turn it like this, they look like jellyfish. Who's thinking of Finding Nemo right now where they're jumping on the jellyfish? I know I am. All right. So those are all going to feed into a single OR gate. And again, I'm fine with you just drawing a single OR gate. So there's 1, 2, 3. And this would be my output. So again, this one's my A naught B C line. This one's my A B naught C line. This one's my A B C naught line. And those are all feeding into this OR, so they're all be adding together, and they're giving us this output. All right, so again, this sum of products algorithm we can use to turn any truth table into a Boolean expression, and then eventually a circuit diagram that we'd actually be making with wires, gates, and transistors and everything else to get a computer to produce a specific behavior. So what's a specific behavior that we might want to produce? Well, we might want to produce a circuit that can add numbers. So you might be asking yourself, I don't know how to add. What does add mean? All right, so let's go back and let's do a little addition lesson, going back to probably like second or third grade. So if I'm adding these numbers, I would say, oh, 8 plus 7 is 15. So I've got a 5, and then I carry the 1. And then you say to yourself, all right, 4 plus 2 is 6, plus 1 is 7. And this time I don't have to carry anything because there's nothing, it didn't go above 9. And then I would say 0 plus 8 plus 16. Well, that's 14, but then I have to carry the 1, and these are both zeros. So this is 1, 4, 7, 5. All right, so adding. Crazy, right? Well, it turns out we can do the same thing in binary. All right, in binary, 1 plus 0 is 1. 1 plus 1 is 1, 0. Don't you dare say 10. 1 plus 1 plus 1 would be 1, 1. Don't you dare say 11. Okay, so if we had two big binary numbers here, how would we add them together? Well, we would say, all right, 0 plus 0, that's 0. Right? With a carry of 0, nothing carried over. 0 plus 1 is 1 with no carry. 1 plus 1 is 0. Wait, it's 0. No, it's 1, 0. So it's 0 with a carry of 1. 1 plus 0, 0 is 1. 1 plus 1 is, again, 0 with a carry of 1. Oops, I forgot to write my carry here. There's a 0 carry there. 1 plus 1 plus 1 is 1 with a carry of 1. 1 plus 1 plus 0 is 0 with a carry of 1. And then 1 plus 0 is 1. So if you were to add 1, 1, 0, 1, 1, 1, 0, 1, 0, 0 to 1, 1, 0, 1, 1, 0 in binary, the answer would be 1, 0, 1, 0, 1, 0, 1, 0. You got all that? That's like clear as mud, right? So we can start to say, like, all right, there's like a pattern here. When I have a 1 and a 0, I need a 1. Right? When I have a 1 and a 1, I need a 0, but then I have to have a carry. When I have a 1 and a 1 and a 1, then I need a carry and a 1 here. And we can start to think of this as like, all right, well, can we turn this into a truth table? Is there a situation here where we could make circuits that would produce this sort of behavior and manipulate the 1s and 0s in the way that we want to manipulate them? So the result of adding 2 binary digits could produce a carry value. So here's our truth table. Right? We've got 2 outputs. One output is the sum, one output is the carry. So 0 plus 0, the sum is 0, the carry is 0. 0 plus 1, the sum is 1, the carry is still 0. All right? 1 plus 0 is 1 with a carry of 0. 1 plus 1 is 0 with a carry of 1. Right? You almost have to look at these backwards. 1 plus 1 is 1, 0. 0 plus 1 is 0, 1. 1 plus 0 is 0, 1. 0 plus 0 is 0, 0. So these are our inputs. These are our 2 outputs. Right? And what we just did, without you realizing it, was we basically just described a half adder, a circuit that computes the sum of 2 bits and produces the correct carry bit. All right? And hopefully now you're having that eureka moment of, okay, we need the computer to perform certain tasks. Those tasks are really just certain combinations of 0s and 1s. So we can design circuits that conduct the operations and produce the behaviors that we need the computer to do. All right? So let's create a half adder. All right, so we just basically did this. We saw that the sum is going to be 0, 1, 1, 0. And the carry is going to be 0, 0, 0, 1. So we're going to use that sum of products algorithm that we just talked about to create a half adder. Okay, well, sum of products, this is not A and B. This is A and not B. So for this sum part, we could create a circuit. All right, we could say not A. So there's my little not A, and feed that into an AND gate. And we could feed B into that same AND gate. See, the lines are going to crisscross here, so that's why I normally don't like doing it this way, because they crisscross and it gets a little messy, but we're going to deal with it. All right, and then I could make another OR gate, another AND gate. And this one is A and not B, so now A is going to come down here. Now, it is important that I do this before I go into that NOT gate, because I want it to just be regular A. And sometimes when you cross lines like this, you'll actually see somebody go like this. They'll put in like a little loop. And that little loop there, instead of drawing it straight across, you'll have that little loop, so it's easier to see that it's going across. And then we're also going to need a NOT B. So There, I've got my little triangle. There's my not B. And then I can feed those two into an OR gate. All right. And then that can go and be my sum. Right? These are my outputs. Now the carry is even easier. Right? The carry is there's only one that's true. The only one that's true is A and B. That's just an AND gate. Right? There's nothing we even have to OR together because there's only one. This is just a simple AND gate. So the carry is an AND gate, and the sum is this combination right here. Now, if you've been paying super close attention, you might also notice that what we just built was an exclusive OR gate, right? Because this was the table for exclusive OR that we looked at earlier, right? When the two inputs don't match, we get a 1. When they match, we get a 0. So this right here is effectively how you would create an exclusive OR gate. All right, but now with this, we can sum two digits. All right, we just taught a computer how to sum two digits by wiring up these gates in a specific fashion to produce the behavior that we wanted to produce. All right, and this carry bit ends up becoming the input to the sum of the next digits. All right, so this carry is then going to go into another circuit so that it can be added to the next two digits that come along. Which brings us to the full adder. So the full adder lets us do everything we just talked about. The carry in becomes an input so that we can add it to the A and the B. And if we string a bunch of these full adders together, we can start adding larger and larger binary numbers. We don't just have to add 2 bits. We can add 16 bits. We can add 32 bits by stringing these together. All right. So the carry in, again, that's coming from the sum of the previous 2 digits. And then the carry out goes to the sum of the next 2 digits. All right. And this would just be your circuit. This would be your sum circuit. We're not going to draw the whole thing in there because we're going to run out of space. And this would be your carry out circuit. Question is, what do those circuits look like? Well, we can figure out what they look like because here's our truth table. And we have a way of figuring out circuits from truth tables. All right, so if we were adding these together, 0, 0, 0 is going to be a sum of 0 with a carry out of 0. 0, 0, 1 is going to be a sum of 1 with a carry out of 0. 0, 1, 0 is, again, going to be a sum of 1 with a carry out of 0. 1 and 1 is going to be a sum of 0 with a carry out of 1. So again, you almost have to read this in reverse. 1 plus 1 is 2. 2 in binary is 1, 0. All right. 1, 0, 0 is going to be a sum of 1 with a carry out of 0. Again, 1, 0, 1. 1 plus 0 plus 1 is going to give us a sum of 1 with a carry out of 0. Again, read it backwards. There's your 2. 1 and 1 is going to be a sum of 0 with a carry out of 0. Again, read it backwards. There's your 2. 1, 1, and 1 is going to be a sum of 1 with a carry out of 0. Again, read it backwards. That's a binary 3, just like we would expect. So we could now go in and make a sum of products algorithm, right? If we wanted the circuit for the sum, it would be not A and not B and C, plus not A, B, not C, plus A, not B, not C, plus A, B, C. Now, could that circuit be simplified? Yeah, it can probably be simplified, but our sum of products algorithm would just be ANDing this row, this row, this row, and this row together. All right, same thing for the carryout. All right, it would just be ANDing not A, B, and C, plus A, not B and C, plus AB, not C, plus ABC. And again, could that be simplified? Yeah, it could be simplified, but that will work. All right, those series of gates would allow you to add these digits. And if we start stringing those together, we can add larger and larger and larger and larger and larger numbers. So let's see what it looks like when we start stringing those together. All right, let's see what this process would actually look like. So I've got my different values here. All right, let's pretend we are adding two different 3-bit values. All right, so we're adding two 3-bit numbers. So bit 1, bit 2, or bit 0, bit 1, bit 2, bit 0, bit 1, bit 2, and then we're going to end up with a sum that's also going to fit in those 3 bits there. So A1 could become an input to our half adder. All right, this is A sub 0. All right, we would add that to B sub 0. All right, remember the example that we just did. Let's pretend the numbers were 1, 0, 1, and I'm adding to that 0, 1, 0. All right, you can think of that as here's A0, here's A1, here's A2. This down here is B0, B1, and B2. I'm starting off by adding A0 and B0. All right, those are going to give me a sum. All right, that sum is going to be my S0. All right, the sum of these first two digits is going to be my S0. There's also going to be a carryout that then becomes the carry in to my full adder. All right, so again, when I'm adding just two digits, sometimes I'm going to have a 0 here, sometimes I'm going to have a 1 here, but I also could have a carryout, which could also be 0 or 1, so that feeds in to my full adder circuit. Now the full adder gets the carry in, but then it also gets a 1, and it also gets B1. All right, that's the equivalent of me going over to this next line in my addition here and saying, all right, now I'm adding A1 and B1, but I also have to consider, was there a carry from this previous addition? Right, that's what's going on right here. And then again, this is going to produce a sum. That sum is going to become my S1. And then it's also going to produce a carry out, which could be 0 or 1, that feeds in to the next circuit. And then that next circuit gets A2. How can I do this to make it as least messy as possible? Go down this way. All right, this would be my A2. And then B2 is down here. And again, this sum is going to give me my S2. And the carryout is going to go. Now, if you're only set up to receive a 3-bit answer and you have a carryout at this point, we could actually call that the overflow. All right, and you can get an overflow error. So if you are trying to capture your answer in 32 bits, and all of a sudden you have a carryout that's a 1, and you don't have a place to keep that 1, it becomes like an overflow. So this could potentially be an overflow if you don't have the space to store that. So for example, if I was trying to add 1, 1, 1 to 1, 1, 1, I'd be like, oh, okay, well, this is 0 with a carry of 1. This is 1 with a carry of 1. This is 1 with a carry. If this doesn't have any place to go, if there is no 4th bit that you've set up to receive that, This can then become overflow if you don't have the space set up to handle it. Now, if you have the space set up to handle it, it's fine, but that's where, we are dealing with circuits that we've created. If we haven't set up the circuit to handle that number, we're kind of out of luck, all right? The computer doesn't just magically create circuits to say, oh, you actually need another circuit here for this to go into? Great. Well, we'll take care of that for you. No, this will probably go into a different circuit, and if it ever hits a 1, the computer knows that some sort of error has happened because it didn't have room to actually do the calculation. But this is how we can start adding numbers on computers, all right? We can create the circuits, and you saw how to create the circuits, all right? We created those circuits. All right, you can create these circuits, you can start stringing them together, and by stringing them together, we now see how we can add numbers in binary. Right? And we could string together different circuits to subtract numbers. We could string together different circuits to multiply numbers. And what we saw in Unit 1 is that everything is numbers. All right, a picture is a sequence of ones and zeros. A sound wave is a sequence of ones and zeros. A picture, text, it's all ones and zeros, it's all numbers. And now we're seeing how we can manipulate those numbers to produce the behaviors that we want to produce. And that's what circuit design is all about. How do we manipulate these numbers to produce the effects that we want to produce? And this is just a glimpse of it, all right? And again, this is an intro to computer science class, so we're not going to go much deeper than this. But this kind of peels back the hood and shows you what's possible and gives you a little insight into how we can actually get a chip to do what we want it to do just by passing electrical signals through wires and gates. All right, so I hope this was illuminating. I hope you found this useful. And again, always reach out if you have any questions, comments, or concerns. All right, have a good one.